Today's class, basically, we are going to look at regular semigroups. To be precise, we are going to look at characterization of Green's relations on the regular semigroups. Uh, I will begin this lecture with the following remark that if S is a regular semigroup, then we notice that an element A in S is always can always be written as A is equals to AXA. And of course, the XA here, we can look at it as just one element so that we have A is equals to A into XA. This XA is an element of S. So since it's an element of S, then A multiplying this element in bracket will be an element of AS. So basically, what we are trying to say here is that A is always in AS, meaning that pick an arbitrary element in a semigroup S, A is an element of A multiplied by S, meaning that A is always an element of the principal right ideally generated by A. So the issue here is all the time A is in AS. Of course, by this, S do not need to have 1, meaning that we don't need identity to be in S. So if we don't need identity to be in S for A to be in AS, then the regularity have simplified the earlier version of characterization of the Green's relations. So meaning that A is in AS, and similarly, A can always be in SA, and it can always be in SAS. And with this, we can just drop all reference to S1 in describing the Green's equivalences on a regular semigroup, meaning that if a semigroup is regular, the reference to S1 need not to. You don't really need an identity to be in S for you to give the definition of the Green's characterization. So, in a nutshell, we have just this definition. Instead of using S1, we can just use our semigroup S. So we have this. Let S be a regular semigroup. For A be in S, so you see A is L related to B if and only if instead of S1A, we just write SA SB, meaning that if and only if A and B generate the same principal left ideal, and R like this and G like this. So meaning that in a regular semigroup, you don't need to make any reference to S1. So if you are dealing with a regular semigroup, you don't need identity. If it is there, fine. If it is not there, it's not. You don't need to adjoin it to S. So as long as you are dealing with a regular semigroup. So this is one of the remarks we are going to begin the lectures with. So now we have the following proposition that let A and B be elements of a regular semigroup S, then A and B are L-related if and only if there exists A prime, which is the inverse of A, and B prime inverse of B, such that these idempotents are equal, meaning such that A prime A and B prime B are the same. We have seen in our previous lectures that A prime A is always an idempotent, where A prime is the inverse of A, and likewise B prime B is always an idempotent, where B prime is the inverse of B. So all we need in a regular semigroup is A and B are related if you have the inverse of A and the inverse of B, such that A inverse A, the idempotent this, and the idempotent this B inverse B in this order are the same. So very nice characterization. Similarly, if that of the R, so we expect to have A prime instead of A prime A. So it change position. So it's in similar fashion, and moreover, H as H is the intersection of the two, we expect the two A prime A because B prime B, this idempotence, and A prime A prime because B B prime to happen here because H is the intersection of L and R. So that's it. So in a regular semigroup, this is what you need. It looks like a special case of the earlier proposition in our first presentation, and it simplifies the two conditions. Instead of having the two conditions, the other one you can just have this. You can just have this because we know that every regular element have an inverse. So if it has an inverse, as long as the inverse satisfies this, inverse of A satisfies this, and that of B satisfies this, and if they are equal, fine. Then we can just simply say A and B are L related. So we can demonstrate one of the proof here. Here, looking at the first one, number one, you can see A and B are along this column. So A and B are L related. And one thing you need to note is here is that A prime, the idempotent A prime A is here. If A prime A is always an idempotent, and we know that A prime A is always related to L A by L. So we have seen that in one of the previous proposition. So this is saying that if you have an inverse here in this class such that B prime and A prime A, B prime B and A prime A are equal. Once they are equal, then certainly A and B are L raised. So this is the pictorial from the egg box characterization of L. So we have seen this from the first one. So here we can prove this result by first assuming A and B are L related. Then if A prime is here, is an inverse of A, then certainly A prime A is an idempotent in this class. We have seen that in the previous, I think the first, the second, the sixth lecture or seven, that A prime A is an idempotent in LA. And since A and B are L related, then LA is LB, meaning that A prime A is also in this LB class. So in the equivalence class of B with respect to L. So, and the R class RB contains at least one idempotent. Thus follows by proposition 2.3.2. If you look at lecture 7, you may refer to slide 16, that automatically once A and B are L related, then this R class of B contains at least one idempotent. We call it E. And that's why here in the previous egg box, you see in this class, it contains one idempotent E. That follows by that proposition 2.3.2. And then we can also apply theorem 2.3.22, also lecture 7, slide 22. You can refer to that. The H class, this A prime A intersection, this contains an inverse P prime. We have proved that in the previous lectures. That is contains an inverse P prime of B. And it has this property. A prime A is equal to B prime A. We have seen that from the previous quotation. So, and also, of course, B prime is E. B prime is actually E. So, and B prime is E, is not the B prime B here. You need to refer to that theorem and see what we are talking about. That that particular R class contains idempotent E, where B prime is the inverse of B, and that B prime has this property, and then B prime is actually the E. So similarly, we need to notice that by this proposition and this theorem, we have actually proved even a stronger condition, because here we pick A, we say let A prime be in V of A arbitrarily. So by picking A prime in V of A arbitrarily, such that all this happens, what we have just proved is if A comma B is in L, then it means that for all, because we pick A prime arbitrary in view of A, so it means that for all A prime in view of A, you can find B prime in view of B such that A prime A is equal to B prime B. That's what we have proved there. So conversely, so we have proved the false. So conversely, we suppose this condition happens for some this and this here. Then if A prime is the inverse of A, then we can have this, because there are two of them. You are going to have A prime A is equals to A. And you also have A prime A prime will be equals to A prime, because their inverse is the inverse of A is also the inverse of A prime. They are inverses of one another. So surely if A prime is here, we'll have this. Out of those two conditions, we can have this. And at the same time, we can associate A prime and A to have A into this element A. And similarly, because A prime A is an idempotent, so you can have A prime A is A prime A prime A, meaning that A prime A square is equals to A prime A. But you can associate A prime A prime like this, and A is outside. So by looking at this, because we have this from here, automatically we have this too. If this, because we have seen that this is an idempotent and A prime is the inverse of A, so we can have this too. But you can see the way a manner this is colored. You can see the way a manner this is colored. And you can see it is here. And again,
Hello.
hello, can you hear me? Hello? Hello?
Yeah.
Hello?
Yes,
Hello?
Doc,
Are you with
we
me?
can hear you. We are
You
with
can
you,
see
sir.
it. Okay, 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 all right, all right.
We can hear you, sir. We are hearing, sir.
Okay. So now, so you can see here in this bracket, we put A prime A in this bracket, and it is here A prime A, and you can see the other A here, different color, it is here. So we can regard to this as just one of the element of the semigroup, and regard to this as another one of the element of the semigroup. So from these two conditions, one can see that A prime A are related by L, meaning that A and A prime A, this idempotent, are L related. So that's it. And similarly, we can also, in a similar fashion, see that B prime B is L related to B. So using theorem. So now using theorem 2.3.4, that's number one. But you see A prime A and B prime B are equal. They are equal. So if they are equal, you can replace this B prime B by A prime A here, so that you have A is L related to A prime A, and A prime A is L related to B. So by that, one can easily see that A and B are L related. So because, but that's by transitivity, because L is an equivalence relation. So you see, it's we have A and B are L related. So we have proved the converse. The meaning that whenever you have these conditions, A and B will surely be L related. So the proof of the second and the third one are similar, and that of the second is even there in the text, and the third you can also deduce that. So the next result we are going to talk about. First, let us look at these preliminaries. Then let U be a sub semigroup of a semigroup S, and U not necessarily be regular. No, U might not necessarily be regular semigroup. We shall denote this symbol A comma B in LU, and the U here to means that you can have some elements U and V in U1, because U is not necessarily regular. You can have U comma V in U1 such that these conditions happens. It's as if we're restricting A, B to be elements of U. It's just like forgetting about S and just defining the characterization of L in U. So But U, don't forget U is a sub-semigroup of S. So even the A and B you are picking from U are also elements of S. So, and similarly, this existence of U and V in U1, U1 is also a subset of S1. So the U and V can also fall inside S1. So while this notation AB in LS to mean there exists ST. Now ST is in S1 such that these conditions happens that SA is equals to B and TB equals to A. So the two notations we need to be familiar with this, and from this notation, okay, we shall also use the notations for the equivalence classes. That is, by saying LAU, it means the collection of all elements in U that are related to A by LU, by the way and manner we define this LU. So U in U such that U and A belongs to LU. Similarly, LAS to mean that S in the larger semigroup S such that A and S are L related and the L is in S here and here the L is in E. So from this a brief introduction, one can notice that if A comma B is in LU, it means there exists UV in U1. All right, UV in U1 by this definition, such that these conditions happens. But then, i.e., that is to say that there exists UV. That same UV we are picking from U1, we can say there it is in S1 because U1 is a subset of S1. So UV in S1, of course, this is the reason since U is a subset of S, such that the same conditions also happen. So what are we saying? By looking at this definition, we are just saying that A comma B is in LS. So meaning that every two elements here that are L related in U will surely be L related in S. Okay, so notice also that A comma B is in U. And if A comma B, because the A comma B, we are actually picking them from the sub-semigroup. So if A comma B element of U, then the pair AB will be element of U cross U, that is the universal relation on U. This pair will be element of the universal relation. So what we have seen that if A comma B is in LU, AB is in LS, and A comma B is actually in U cross U, meaning that A comma B will be in the intersection of this. Because it is here, then we can say A comma B is in the intersection of LS intersection U cross U. So basically, what have we demonstrated? We demonstrated that if A comma B is here, then it is here. And that means that LU is a subset of this intersection, LS intersection U cross U. So we just conclude this. So and similarly, others will follow suit. That is the R, even the D, the H, and the J. They will always be subset of RS intersection U cross U all the time. So as an easy exercise, using the infinite cyclic group S, one can demonstrate generated by A and U to be the infinite monogenic subsum of S generated by A consisting of course all positive powers of A. One can actually show that on this sub-semigroup U, LU is RU, they are all the same. And it's nothing but the identity relation. The identity relation, that is the diagonal relation on U. So you can show that. And that, of course, on this infinite cyclic group S, this and is equal to this is equal to this. They are all the same and is the universal relation on U. So note that this from this example, we're saying that on the sub-semigroup, that is LU is just I of U. But here, it is not I of U. LS intersection U cross U is not I of U, rather is U cross U. And it is very clear that IU is a subset of U cross U because this is just the diagonal relation, the identity relation on U is always a subset of this. So basically, all we are saying, and not this is strictly subset here. This is strictly subset of U cross U. So we are saying that LU is strictly subset of LS intersection U cross U. So basically, the point we are trying to make using this example is that the inclusion there can be strict, can be strictly contained, meaning that you can have, using this example, one can show that the inclusion is strict. It may be strict. So that's it. So this means that the inclusion can be proper. So here, meaning that you may not have equality. LU can be strictly with this subset of LS intersection, and the rest will also follow suit. So now we have the following proposition that if you, the point here, what we have seen earlier is that it can be inclusion and the inclusion can be strict. And then the next question one should ask is, can it be equal? Can the two be equal? So the equality is here in this particular proposition that if U is a regular subsemigroup of a semigroup S, then you are going to have equality. You are going to have equality. That is, LU and this are equal, and this are equal. Basically, what this, before we prove this proposition, what the proposition is talking about is that if you have a regular subsemigroup of a semigroup S, then the characterization of L, R, and H for the subsemigroup will just be the same as the characterization of L or R or H of the mother semigroup S. Meaning that if you are here, if you are certain that U is regular and you are aware of the characterization of the Green's relation of S, then you can just adopt it in U, meaning that you can inherit that. But that happens only when you are dealing with a regular subsemigroup. Of course, if U is not a regular subsemigroup, this inheritance is not true. And also, this inheritance is only L, R, and H. Nobody talks about J or D. No. D is not necessarily true. It may not necessarily, even the regular semigroup may not necessarily inherit D. I think we will see one of the examples soon in some of the subsequent slides. So this is telling you that if you have U, a subsemigroup of S, and U is a regular semigroup, subsemigroup, if we are aware of the characterization of the Green's L and R relation of S, then it can be adopted on U, meaning that U can inherit those characterizations. However, if U is not regular, that is not actually the case. So now let us demonstrate one of these, and I choose to pick the R. I think that of the L has been proved in the text. So we have seen that RU is a subset of RS intersection U cross U. So now it is enough to show that RS intersection U cross U is a subset of RU. All right? We show that the bigger set is a subset of RU. And once we show that, then the equality will just happen. And then to do that, we can pick an arbitrary element from this set, RS intersection U cross U, A comma B, and try to show that A comma B is also in RU. So now we pick AB here, and we let A star and B star be the inverses in U, inside U. Don't forget, U is a regular semigroup. So if you pick AB in RU, B has an inverse, A has an inverse inside U because U is a regular semigroup. B also has an inverse inside U because B is a regular semigroup. We don't know who is S. S might not even be a regular semigroup, but we are sure that U is regular. So the A and B we're picking them from U, so surely they will have inverses. So we let the inverse of A to be A star and that of B to be B star respectively. Then we are sure that A star is an idempotent because it's clear. It's an idempotent and is related to A by R. And this element is in RS. Of course, it's in RS. And similarly, BB star, comma B will also be in RU. And we are sure that this element is also a subset because RU is a subset of RS. So, and so the two elements A star, B star will be related in RS because you can see that A star A star A is in RS, B star B is in RU, then certainly A star and B star, this and this, will surely be in RS. The two idempotent will be related there. And by proposition 2.3.3, each of these guys, this and this, is a left identity on LAS LB in S in the bigger semigroup. That is, A star will be a left identity for every element inside this class. B star will also be a left identity for every element inside this class. And of course, the classes are the same since A star, these idempotents are actually element of RS. So, and in particular, because the two elements are inside the set themselves, so we can pick a particular case that is A, if you pick B star from here, then A star multiplied by B star will be equal to B star because A star is a left identity element inside this. So for every element here, you have this condition. So in particular, if we pick B star, we multiply A star by B star, we're going to have B star. Considering A star as left identity. Similarly, considering B star as left identity, I can pick A star inside this class, and we are going to have B star multiplied by this operation. This is going to give me A star. Why? Because B star is a left identity. So one thing you need to note is that the elements here we are dealing with the elements of U. We did this A star, B star, they are all elements of U. They are all elements of U. And so may be interpreted as implying that if you look at this, that A star, comma B star is in RU, meaning that you see A star is equals to some element B star, and B star is equal to some element A star, meaning that B star and A star are related in U because basically they are in U, elements of U. So, but don't forget, we have A, comma A star is in RS, right? And A star, comma B star is in RU. Again, B star, comma B is in RS. So we can conclude this that because here, okay, here is supposed to be a U, and here is supposed to be U. So not S, please, here and here. I'm referring to this RS is RU, RS here is RU. So if you look at what we have here, A star is in RU, A star, B star is, so you have A star here, A star here. So you can just say A comma B star is in RU. But also B star comma B is an RU. So one can conclude that A, because by transitivity, actually, by transitivity, that A and B is in RU as required. So really, we pick A comma B here, and finally A comma B is here. So what are we trying to say? We are trying to say that this set is a subset of RU. And the proof of L is actually the dual while H follows from L and R. So we have proved the result. So just like what I have said earlier, that the corresponding assertions for these relations D and J are not generally true. And there is an example there to demonstrate that. For example, if we consider the semigroup B2, this B2 is there. You can check section 1.5 at the end. I think it's in page 32 to 33 of the text. B2 has 1, 2, 5 elements. It's a semigroup with 0 and it's having this multiplication table. Of course, it is clear that B2 is a regular semigroup, and the reason is because 0 is an idempotent, A is a nilpotent. You can see A multiplied by A gives you 0. It's a nilpotent, and nilpotent is also a regular element. So B is also a nilpotent, so it's also a regular element. E is an idempotent. E is E. So, and all idempotents are regular elements. Similarly, F is also an idempotent. So, and of course, we can even see that A and B are inverses of one another, meaning that A is ABA. You can check that from the table, and B is BAB. So they are inverses of one another. So, and you see inverses elements are actually regular elements. So it is easy to clarify that this subset U with 3 elements, 0, E, F, is a semi-lattice of idempotents. Pause, 0 is an idempotent, E is an element, and F is an idempotent. And since it's a semi-lattice of idempotent, we know in a semi-lattice of idempotent, the characterizations of L and R and the rest, we have seen it is trivial. 2 elements, L or R or H or D or J related, even only if they are equal. So basically, we are going to have this, so meaning that all the characterizations here is just the diagonal relation, I1 on U, the identity relation, okay? So we have seen the characterization of the Green's relation on U. So now let's see on the other hand to see what about RS and intersection U cross U. On the other hand, it is easy to check that the RS classes are this. It has just 3 classes, and the LS classes are also this. One can easily compute that, and hence DS classes are 2. We are going to have 2 classes. So you see the DS here, we only have 2 classes. And the DS in the previous one class, because it's a trivial relation, surely you are going to have 4. Because here is a trivial relation, and element is only related to itself here. So the DS classes, you are going to have 4 of them. And here you see the DS, there are only 2 classes, 0 and this. So what we are saying in the previous one, the DU, there are 4 classes, the DU. And here the DS, there are 2 classes. So now we are dealing with a finite semigroup. G and S will be the same, since B is finite with just 5 elements. Thus, from here, we can see that E and F are related because they belong to this class, E, F. They are here. They belong to DS, intersection U cross U. And since G and D are the same, it also belongs to this JS, intersection U cross U. But then E, F is not an element of U. I think here I'm supposed to write DU, not please US, noted that. So this is supposed to be DU. It is not in DU because the earlier relation we gave for D is just the identity relation on here. So meaning that in U, E and F are not D related. In U, E and F are not D related. But here in S, E and F are actually related. So clear, it is clear that the two sets are not the same. The two sets are not equal. So that have shown you that yeah, that a regular semigroup A of a semigroup S inherits the factorization of both grace L and R equivalences of subgroup S, but not necessarily D and G, meaning that you may have a regular subsemigroup, it will inherit L, it will inherit R, but it may not necessarily inherit D. This is one of the criteria. The next thing we are going to discuss is that if S is a semigroup and E is the set of idempotents of S, then we shall say that an equivalence rule on S is idempotent separating if rho intersection E cross E is IE. That is, what are we saying? If no row class contains more than one idempotent, meaning that once you intersect this row with this, you are just going to have the diagonal relation, which is I on E. So whenever you intersect any equivalence on S with E cross E, provided that the semigroup have set of idempotents, then we refer to that rule, which is a congruence on, an equivalence on S. We refer to it as idempotent separate. And we shall see, we can see that by corollary 2.2.6, you can also see lecture 7, slide 12. You remember that no H class in S contain more than one idempotent. We have seen that in our previous class. And if this is true, then one can conclude that H is idempotent separating for any semigroup S. So the trivial example one will give for idempotent separating congruence is the relation H. The relation H is always idempotent separating for any semigroup S. So it means that any congruence contained in H must be idempotent separating, because the H itself is idempotent separating. And if you can have any subsets of H, which is a congruence, will surely be an idempotent separating. In fact, we have even the following proposition that if S is a regular semigroup, then a congruence on S is idempotent an element. I think this is a subset, sorry, if and only if rho is a subset of H. So here, the proof, the forward follows from the above remark, and the backward, while the converse follows from the Lallemant's lemma. So and you can just see that from the previous lecture, slide 19, or you may decide to see the text, page 57 actually. The assumption S is regular cannot be removed from the above proposition. Here, you see here we said if S is a regular semigroup. If you remove regularity, then the proposition may not necessarily hold. It may not hold. So we require S to be regular. So we can demonstrate that the assumption cannot be removed if we consider this null semigroup. That is this semigroup with two elements, where 0 is the zero element of the semigroup and x square also gives you 0. So we can see that x squared is equal to x times 0, and it's equal to 0 times x, and it's equal to 0 times 0, and it's equal to 0. Then 0 is the only idempotent, because 0 square will give you 0, but x square is not going to give you x, rather it's going to give you 0. So 0 is the only idempotent element. And since 0 is the only idempotent element, then the H class is just the identity on S, I on the S. So you see the universal congruence, this is then idempotent separating, because here S cross S, we are going to have x0, 0x, 00XX. So it's only idempotent separating, but not contained in H. It's not in H because H here is the identity relation on S. So H is just 00, X, X as a relation, while the universal congruence S cross S is going to have four elements. So this is one of the examples that shows that you can't remove regularity. That is, S need to be regular. You can't remove it. So we have seen that the concept of inverse in semigroup is the generalization of the inverse A inverse of an element A in a group G. So within a group, we have this very useful property that AB all inverse is equal to, this is also B inverse A inverse, so it's supposed to be B inverse A inverse. And we know that AB all inverse can only be equal to A inverse B inverse if G is abelian. So this is a very useful property in group. So one may it's reasonable to ask a question whether the version of this type of result hold in irregular semigroup. In general, it is not the case that the set of inverses of AB is equal to the set of inverse of B multiplied by the set of inverse of A. However, it has been proved that this inclusion is true for all AB in S if and only if E of S is a subset group of S, meaning that this inclusion holds if the semigroup is orthodox, meaning that the set of idempotents form a subset group. However, if the set, because it is not always true that set of idempotents of a semigroup forms a semigroup, it's not always true. It's not necessarily true. There are a lot of examples of that. So, so for a generalization that works for a regular semigroup, we want to see a similar result, but it looks like something more general. It doesn't look like AB all inverse cross B is A. But for that, for something that work in some sense, we need the following concepts. So, the concept here, we start with this proposition that let S be a regular semigroup with set E of idempotents, and let E, comma F be in E. Then this set define this, that is the collection of G, where G is the inverse of EF, and at the same time G is an idempotent. So we are only meaning that this set contains idempotents. It has to be the inverse of EF and it must be an idempotent. Because you can have an element which is not an idempotent and it's in the inverse of this. So we are restricting ourselves to idempotents. Such that these conditions is satisfied, meaning that GE is equals to FG. So it's like we are commuting G with the E here. So instead of E here now is F. F is coming in place of E, commute with G, and it gives you back G. So this more or less looks like, because if E and F are equal, we are going to have GE is equal to EG is equal to G. So it's as if E is serving as sort of identity if E and F are the same. So the claim here is that in a regular semigroup, this type of set is not empty, meaning that you can always find an element in this type of set. Pick two idempotents, E and F in E. Define this set, you usually have at least one element in the set. So let us demonstrate that. Uh, uh, let us pick an X, an inverse of EF, and let G be this product. So you can see here we try to push X to be in the middle of FE. So G is pushed at the middle here. So G is equals FXE. So what is our claim? Our claim here is that this G belongs to the intersection of V, E, F, and E. That means that G is the inverse of EF, and also G is an idempotent. So let's let us see that. Note that to prove that G is an idempotent, EF to be equals to EF, and we need GEF G to be equals to G. So let's start with this EFGEF, and we know the G we denote it to be FXE. So you see you have EF, FXE, EF, and here E and E here. Now F square is F because F is an idempotent. Likewise, E square is E. So you end up with EFXEF. Now associate these two guys here and the other two guys here. So you have EFXEF. But who is X? X is the inverse of EF. So if X is the inverse of EF, EFXEF will surely be EF. And so you have seen that we have shown that EFGEF is EF. So similarly, GEFG is equals to who is G? FXE, F square, and of course E and F are both idempotent. So we have this FXE, FXE. So you see we can write this element as this, meaning that we are associating. So we allow X to be outside, X to be outside here, and EF to be in the middle. So the content here of this bracket, don't forget that X and EF are inverses of one another. So if they're inverses of one another, you can write this product will just give you X. So you have FXE. And who is FXE is what we denote to be G. So this is telling us that G and FX and EF are inverses of one another. And that means that G actually belongs to this set. It always belongs to this set. So, and so G here, G is here. Now also, G, we said G is an idempotent. So we need to compute G square and see whether it is going to give us back G. So here G is G times G, which is FXE, FXE. We can also associate here E and F together, X, E, F, X. Now, X and EF are inverses of one another. You will be left with just X. So here you have F, X equals G. So it means G is an idempotent. So meaning that quite sure the G we pick is element of this set. Now we want that G to satisfy this condition. That is, will GE be equals to FG, and will it be equals to G? So that's what we are going to see. Uh, so now G multiplied by E is FXE multiplied by E. So you see you just have FXEE, which is E square, and E square is E. So you still get back your FXE, which is G. So it means GE is G. Now FG also, you see, is F multiplied by FXE, so, and F square is F, so we have FXE, we also have G. So it means really G satisfies this equation, i.e. GE is FG is G, and that is telling us that G is an element of this set. So at least we have demonstrated that we can always find one element in the set, and that is telling you that the set is truly not an empty set. And we have proved this result. So now, since we have proved this result, we would like to call this set what? We call it sandwich set. That is, the set SEF is called the sandwich set of E and F. Similarly, you can demonstrate that instead of the earlier characterization SEF given like this, you can just simple exercise to show that you can just say, okay, the collection of all E comma F such that G is in E, because we want only idempotents that satisfy this condition. That is, GE is equals to FG is equals to G, and EGF is EF. So this and the earlier sets are equivalent. You can deduce that. So it has this characterization. The sandwich sets have some links with the crystallization of L and R on the idempotence of a regular semicolon, meaning that there is a link between L, R with this set. And that link is as follow, that if you pick E, F, and G as idempotents in a regular semigroup, then if E and F are L related, once they are L related, these two sets will be equal. And you can see the way and manner the sets are written, that is SEG will be the same as SFG. So you can see the G here is on the second coordinate, while the E and F are on the first coordinate. So, and that of the R, you expect to intersect, to interchange the position of the G. So this is exactly what is happening. That is, whenever the two idempotents are L related, then this type of sets will be just be the same. So, and the proof is as follows. It is enough, of course, once you show one way, the other way will just follow in a similar way. So I will just prove one of the ways. So to show this, we can suppose, so I also pick, I think two, maybe that of one, we may check the previous two. So suppose E comma F is R, and I pick a T here in SG coordinate. So if so, I'm picking T in this set. So I want to see whether T will be here. Once T is here, it means this set is a subset of this set. And if that happens, the other way around will just be dual, the same. So uh, because E and F are related, this will follow. Fe is E, EF is F. And T belongs to this set. We can use this characterization to just write ET is TG is T, and GT is equals to GE. Yeah. Then we can start from T, which is this, which we knew it to be ET, and this is equals to who is E. I see use this color. E is actually FE, so I replace E with FE, then you end up FET. And you can associate E and T, you have ET, but ET is actually T. So what did we have? We have T is equals to FT. And GTF is equal to, so who is F? F is EF here. So you see that? F is EF. Next, we associate GT and E together, F outside. And then GTE is actually G. So instead of GTE, we just write GE. So here we remove G, so it will be GEF. So you can also associate E and F like this. And who is EF is F. So you have GF. So you see, we have E is equals to FT, GTF is equals to GF. So what do we have? At long run, we just have that T is an element of SGF. So we pick a T here, and we have demonstrated this is here. So, and now the result actually follows. So the next result is that this sandwich set is not just an ordinary set. It has a structure in it, meaning that it is actually a subset of S. So it's not just an ordinary set, it has a structure. It's endowed with a structure. So, and the proposition is here that let E comma F be idempotents in a regular semigroup S. Then the set this SEF is a subsemigroup of S, and not only that, it's a rectangular band. I'm sure in one of the previous lectures by Dr. A.S. Imam, A.T. Imam, sorry, he have discussed about the bands, the rectangular band. So we can demonstrate the proof to show that indeed this set is a subsemigroup. So to prove it is a subsemigroup is to show that is to pick two elements from the set and show that the product is also in the set. Now, if you pick GH here, then GHG it can be written as GHHFG, and This can also, because G is already here and H is already here, so using G is GE, you have H in the middle, and G is also FG because G is in this set. So here, we can associate EHF. So we have G is EHFG. So, and EHF is actually EF because H is in this set. All right, so we are using that characterization straightforward. So you have this EHF to be just EF. And now we have GE here and FG here. And of course, GE is G because G is in this set, and FG is also G because G is. So you see, you end up with GG. But G is an idempotent because it's in this set. You just have actually G. So you see, we have G head G is equals to G. So we pick. So this actually G head G equals to G has actually proved that if this set is a subsemi group, it must be a band because this condition one has actually satisfied the condition of a band. If you remember, a band, if you pick three elements, for instance, A, B, C, if you have A, B, C is equals to AB. So it's GG here, like AB, then that set of idempotents, as long as it is a subsemi-group, is a band. So this one actually shows that the set is a band. So now take note. So we have GHG is equal to G. It follows that GH square is equal to GH. And how do you get that? It's just by simply multiplying H on the right of this equation 1. Multiply H here, H, so you have GH is equal to GH. That is telling you that the product is also an idempotent. Okay, that is after multiplying this equation 1 by H on the right. So GH is an idempotent. Also, GHE can be written as G associate HE, and HE is H because H is in the set. So you have HE to be just H. So, and again, F multiplied by GH, you can associate F and G and have H so that FG is G. Why? Because G is in this set, so F multiplied by G will be G. So here you just have GH. So you have FGH is GH, and here you have GHE is GH. So again, E now GH in the middle, EGHF. Let's see what we are going to have. This is going to give us EGHF, but the H itself is FH. The H itself is FH, and here you have EG then FH. You associate EFG then FHF, and this is equal to EG is actually E. So you have FH, EFHF, and then you can associate EF again, and EF is actually E. Yes, because F is actually a right identity for all the elements here. So here you have EF is just E, so you have EHF. From EHF, you may associate E and H, then you may associate H and F. HF is F, so you have just EF, which is this. Uh, so we, and so one of the conclusion, it means we have shown that condition, the two conditions that GH actually satisfy them, and that means that GH, the product GH is in S. And don't forget, we picked the two from SEF, and the product now satisfies these conditions, and GH is in S of E and F. And so it's just like what, so it means S comma EF is a subsemi group of S. And just like I have earlier said, that this equation 1 actually ensures that this is a rectangular band. Yeah, you may as well refer to theorem 1.1.3, which is on page 7 of the text. Okay, so now we have the following result, that let A comma B be in S, where S is a regular semigroup. And if A prime is the inverse of A, B prime is the inverse of B, and G is in S of these idempotents. because if A prime and A are inverses of one another, A prime A is an idempotent. Similarly, B prime B is also an idempotent. So you have this, that G is here. So then the result here we are saying is this combination, meaning that B prime A prime, you see G at the middle, G at the middle. Okay, this element is surely an inverse of AB. So B prime G A prime is the inverse of AB. So in the sense of semigroup, you see in the group structure, AB all inverse, meaning that the inverse of AB is B inverse A inverse. But here the inverse of AB in a regular semigroup is B prime. So as you see, it's like the B has interchanged position, but there is something in between A prime, B prime, G A prime. So that is the generalization. And here we can just give the proof, which is a very short proof. So here we know if we allow this A prime A and B prime, B B prime to be E and F, and pick a G in S of E F, then we can compute this. A B, then put this in the middle, because all we want to show is that this G is the inverse of AB. G is the inverse of AB. So we have to show those two conditions, meaning that G ABGAB is equals to AB, and GABG is equal to G. That's basically what we are going to show. So we start with this AB with this with this inverse AB. We want to see whether this is going to give us AB first. So here we can associate B prime, A prime, and we're going to have F here and E here. And we can associate the middle term FGE. And FGE is going to give us G. Why? Because G is here. G is element of this set, so we're going to have G. So who is A? A and B, you can see A has an inverse A prime, B has an inverse B prime. So we can write this A as A prime A, and we can write B as B prime. Yeah, we can write them like this. So, and here we can associate A prime A, associate B prime, and A prime A is actually E, and B prime is F. So you have AEGFB. So you can associate EGF. Now EGF, because G is in SEF, so GF will just surely give you F. So you end up with EF. Or EG will also give you E, because G is in SEF. So here we have A to be equals to just EFB. And then we know who is A. A is A prime A. E, we know E is A prime, and F, sorry, E is A prime A and F is B prime. So we write the products which gives E and that of F like this. And we can associate A prime A and associate B prime B in this manner. And this is A and this is B. So we end up having B. So you see what we have just proved is that if you put this element in the middle of AB, you are just going to have AB. Similarly, now we need the other way around and see what we are going to have. So B prime GA prime multiplied by AB multiplied by B prime GA prime. We want this result to be just what B prime GA prime. And once that happens, AB and B prime GA prime will surely be inverses of one another, and that's the type it. So now, using the associativity property, which is the most important property in the semigroup, here we can associate A and A prime here at the middle, here, so B, G prime outside. So here also you can associate B prime, here you have G A prime. But then A prime, we know it is E, and B prime, it is F. So we end up with B prime G E F G A prime. But then GE, GE F, maybe GE will give you G, and GEF will surely give you G. So you can say GEFG. GEFG is just a GG, meaning that because G is an element of this set, so GE will give you G, GFG will give you G, so you are going to have GG. So here we'll be left with B prime, GG, A prime, and here G is an idempotent, is here, it's an element of SEF, so you have B prime G square A prime. And this is equals to what? Because G square is G, so you just have B prime G A prime. And so we conclude that B prime G A prime is actually elements, is an inverse of AB as we are required. So this is how it looks like in irregular semigroup, in irregular semigroup, in irregular semigroup. So we are going to end the lectures with this following remark. If the assumption S is regular, in just the above theorem is replaced with S is a group, what do you think will be the conclusion of the theorem? In the assumption there, we assume that S is a regular semi. So what if we remove a regular semigroup and put a strong structure there, a group? So what do you think will be the conclusion? One can just sit down and verify that. And moreover, what will be the sets V of A, V of B, and this set S A prime, A, B, B prime? What will they be? You also have to do that. Again, between and L and R, between sandwich set its relations? I don't know. Okay, so expected that since the researchers was the students all those exercises 60 to 65 of your understanding. In the exercises, you realize you are not understanding these relations if you are given any new class of semigroup. Really, characterizing this Green's relation in so many semigroups is not an easy task, and we must have seen in so many papers published that this characterization is really not trivial. And the characterization is very useful because it gives you the structural property of the semigroup, and other algebraic properties of the semigroup can actually be deduced from this type of characterization. One example is the rank properties. The D classes, characterization of the D class is very, very important in obtaining rank of a semigroup, being it regular or even not regular. So I think we are going to stop here. Thank you for listening. Thank you all. I wish everybody best of luck. All right. Thank you.
Thank you, Dr. Herman said.